Hello students, welcome to FosterJEE. Today we are going to start our first lecture of electrostatics. So let's begin. First of all, we will understand what is the meaning of electrostatics. We can see the word electrostatics is made up of two words, that is electro and statics. Now, what does that mean? We will write electrostatics. Since we know electro is a word derived because of charges, and statics means when something is static or at rest. So, it can be concluded from the name itself that electrostatics is the study of charges at rest. That is, the charge is at rest and it is not moving at all. So, that branch of study is termed as electrostatics. To give a very real life example for something related to electrostatics, so that we can relate that why are we actually studying this subject. Now, we all have noticed that when we rub a comb on a dry hair, it acquires some sort of energy, or we can say it acquires some charge, due to which when this comb is taken closer to small bits of paper, the comb is able to attract or lift some of these bits. Why does it happen so? Similar phenomena occurs if we rub a glass rod on another amber rod, or we rub it with the cloth. Then also we will observe that the rod is able to attract small bits of paper. Why does it happen so? To answer all such phenomena, we have the branch of study called electrostatics. So we are going to start with our first lecture. Now, first of all, we will discuss what is an electric charge. Electric charge. We can see electric charge is an intrinsic property of protons or electrons, or we can say a matter. Like mass is also an intrinsic property of a matter, which means every matter has some sort of mass. Similarly, electric charge is also intrinsic property of the matter, and hence we can say a matter possesses some charge. So we can write electric charge that it is an intrinsic property of matter. Now we will see how many types of charges are there. Types of charges. So we can say till date only two types of charges are found, that is positive and the other one is negative. Also, the most fundamental particle for carrying positive charge is proton, and the most fundamental particle for carrying negative charge is electron. Both these particles have charge of magnitude E. The difference is proton has a charge of plus C and electron has a charge of minus E. Now what is E? E is the smallest charge smallest charge present on a matter. That is, it is the smallest charge that a matter can possess. In other words, no charge can be lesser than E. Now, what is the value of E? So, the value of E is 1.6 into 10 to the power of minus 19 Coulomb. This means this magnitude of charge is present over electron and proton. Now, what is this C? C is called Coulomb, which is the SI unit of charge. Now, at this point, we will discuss the quantization of charge. Now, I will write a fact that charge is quantized. What does this statement mean? Now, in very simple words, we can say if a particular quantity is quantized, that means the total of that quantity will be an integral multiple of the quantum of that quantity. For example, here charge is quantized. This means the total charge on a body will be an integral multiple of the quantum of charge, and which is E. Or we can say the total charge Q will be equal to n times of E, where n is an integer and E is the quantum of charge. Quantum of charge, which in other words is the smallest charge present on a matter. This means, for example, the total charge on a body can be 1e, twice of E, 3 times of E, up to n times of E, where n can be any integer. Why is that important? Because charges cannot be occur in fraction of E, that is 1.5, 2 by 3 or anything else like 0.7 E. It is just baseless and not possible till now. Why I am saying till now? Because maybe in future or in quantum mechanics this can happen, but in branch of this branch of physics, that is electrostatics, we will assume that charge is quantized and it can't occur in fraction of E. It has to be occur in integral multiple of the quantum of charge. Now we will see some points on charges. Now you can write important points. Important points. First point is like charges repel each other and unlike charges attract each other. like charges repel each other, repel each other, and unlike charges attract each other, attract each other. We will understand this with the help of a small example. Suppose there are two bodies. First body has two electrons and second body has three protons. Now, what will be the total charge on this body? That will be minus of twice of E, because the charge on an electron is minus E. Similarly, what will be the total charge on this body? That will be 3 times of E, because the charge on proton is plus E. Now, since both these bodies have unlike charge, that is, one is positive charge and the other is negative charge, so these bodies attract each other. Attract each other. Now, similarly, if we have two bodies, let's say on this body, one electron is present, and on this body, 4 electrons are present. Now, the total charge on this body will be minus 1 of E, that is minus E, and the total charge on this body will be minus 4E. Now, since both the bodies have same charge, that is like charge, so they will simply repel each other. Repel each other. Now, one more point that I will discuss here is that suppose we have another two bodies. On this body, we have 3 protons, and on the second body, first we put 2 electrons, and then we put 2 protons. And suppose we put 1 electron here also. What will be the total charge on each of the body? That will be 3 proton with plus sign minus 1 electron with minus sign, that is plus 2E. That is, this body will have positive charge. Now, what will be the total charge on the second body? That will be minus 2E because of 2 electrons plus 2E because of proton, that is 0. So this body is neutral. Now, the question is, will they repel or attract each other? Well, since this body is neutral, there will be no effect of any other charge present nearby this body. So, they have no interaction. No interaction. Now, coming to second point about charge, we can write charge is a scalar quantity and two types of positive or negative. That is, charge is a scalar quantity and as we have discussed, it is of two types and is of two types. That is positive and negative. what does it mean that the charge is scalar? So, what we have done in this particular illustration, on putting first initially 3 protons and then 1 electron, the charge will get simply add up without any direction or something like we do in vectors. Similarly, on this body, initially we took 2 electrons and then we took 2 protons. So the net charge will be simply the algebraic sum of both these charges. So this is the meaning of charge is scalar. I hope it's clear. Now, coming to the third point, charge is quantized. Now, we have discussed this very briefly, that charge is plus or minus of negative times, n times of E, where n is integer and E is the quantum of charge. Quantum of charge. The fourth point about charge is charge on an isolated body during any process is constant. We can also write this in another form, that charge cannot be created or destroyed. The meaning of this point is that if we take any isolated body means it is not coming in contact with any of the other bodies present nearby it, then during any such process, the total charge is constant or conserved. Or we can say the charge can't be created nor be destroyed in an isolated body. Now, our fifth point is the basis of studying whole electromagnetism, which include electrostatics, electricity, magnetism, and electromagnetic waves, which we will study in upcoming chapters. The fifth point, it says that a charge at rest produces only electric field. Now, a charge moving at constant speed or, to be more precise, we will say constant velocity. I'll discuss why not speed, why velocity. A charge moving at constant velocity will produce electric field and B magnetic field. Now, third point is, or we can say another case is, a charge moving with variable speed. In bracket, we will write accelerated charge. Accelerated charge. Produces A. Electric field, electric field. B. Magnetic field, magnetic field. And C. Electromagnetic waves, electromagnetic waves. Now we will discuss these points one by one. Suppose there is a charge. It is kept rest, that is, its velocity is 0. Then it will create electric field around it. We will discuss this field, but for the time being, we will say it will produce only electric field around it. Only electric field. The second part of this point says if a charge is moving with some velocity v, which is constant, and the vector is constant, then it will create electric field also and magnetic field also. Now, the direction of magnetic field can be determined after studying magnetism chapter, but for time being we will say that it creates some magnetic field also. That is, this is our electric field and this is our magnetic field. Electric field and magnetic field. Now, we have focused that the direction of the velocity should also be constant. This is because velocity is a vector quantity, so we have to take care about its direction also. Otherwise, suppose if the magnitude of velocity is constant but the direction is also changing, in that case it's an accelerated motion and not moving with constant velocity. So it will fall under third case and not second. So that's why we have to specify the direction also. Now, coming to third case, if a charge is moving with an acceleration, then it will produce electric field, some magnetic field, and it will also generate some sort of electromagnetic wave, EM wave. Now, we will discuss all this in upcoming chapters. But for the time being, our chapter deal with the charge at rest produces only electric field. Now, to study the effect of electric field, we have categorized our material into two categories, that is material which is also called matter. First is conductors, and the other one is insulators. Now, we will differentiate both these by saying that in conductors, electric charges are free to move, whereas in insulators, electric charges are tightly bound tightly bound with their respective atoms. Respective atoms. Now we will see quickly how do we charge a body. That is charging of a body. First is charging by rubbing. Charging by rubbing. Now suppose this is a silk cloth, and this is a glass rod. Suppose initially both are neutral, that is net charge on both is 0. Now what we have done, that we rub both this rod with silk cloth. Now see what happens. Suppose this is our rod. Now it will have some atoms, and the atoms will have some electrons. Now when we rub glass rod on the cloth, due to friction, some electrons absorb some amount of energy and gets ejected out and get transferred to the cloth. Now due to this reason, what happens is this rod creates some deficiency of electrons. Now initially it is stated that both the rod and cloth were neutral. That means number of electrons equals to number of protons. But due to rubbing, some electrons gets transferred from the rod to the cloth. That means number of electrons, this is initially. Now finally what happened? Number of electrons are now decreased, but number of protons are still the same. Now what does that mean? Electrons have decreased. The protons are same in number, that is the protons are now more. It means this rod will acquire some positive charge on its surface. And coming to the cloth, since it have received some electrons, and initially number of electrons and protons on this cloth also were equal, that means after acquiring some electrons from the rod, the number of electrons are now more. That means this cloth will acquire some negative charge on this surface. So this is the phenomena how the charge is obtained on body by rubbing. Since the reason for ejecting electrons is friction, this is also called frictional electricity. Frictional electricity. Now our second method of charging a body is charging by contact. Charging by contact. In this method, what happens is, initially, suppose this is a glass rod, and or else suppose it to be an ebonite rod. Since glass rod has positive charge, for understanding purpose, we took it as ebonite rod. The property of this rod is it can acquire negative charge very much. That is, it can acquire negative charge by any means, Suppose we have rubbed it by some sort of material so that it has acquired now net of negative charge. Now suppose there is an isolated metal sphere. Metal sphere, this is for isolation. Now suppose we take this rod near to this metal sphere and touch it. So what will happen? Just after touching, some negative charge from this rod will get transferred to this. So now this metal sphere will get some of this negative charge. This is an example of charging by contact. Now our third method is charging by induction. Charging by induction. Now this is similar to previous case, just in this we don't touch the two substances. Suppose we have an ebonite rod with some negative charge on it. Now suppose we take it closer to isolated metal sphere. Metal sphere. Initially net charge on this metal sphere was 0. But what happens when we take this rod closer to this? Now as we can see, we have taken this rod closer to this due to the fact that like charges repel each other and unlike charges attract each other. So due to this fact, some of the positive charge, no, initially all the electrons and protons on this metal sphere were distributed all over the surface. Once we took this rod closer to the metal sphere, the electrons present on this side will feel repulsion. So due to this, the electrons will run towards this side. And because of the fact that unlike charges attract each other, the positive charge will remain on this side. Now, here one very important point I would like to mention, that only electrons move. Only electrons move and not the protons. Why so? Because in conductors or surfaces like metal, the electrons are free to move, that are called free electrons. But protons are bound with the nucleus. So the protons never moves, only the electron move. Now the doubt arises that then how come the protons came here after feeling some attraction from the rod? The answer is very simple, that initially in this region electrons and protons were distributed equally over the surface. Once we take this rod closer to the sphere, the electrons will go to this side, whereas the proton will remain this side. So this side means the deficiency of electrons, and this side means excess of electrons. Now I hope this is clear. Now we will remove some of this information to generate some space. Now we can see now positive and negative charges are separated a bit. Now in this instant or in this scenario, what we will do, we will take a wire and connect it to earth. Note, this is the symbol of earth. earthing, symbol of earth. What happens when we connect some charged body to earth? It happens that the excess of negative charge will always flow towards the earth. Now, why does it happen? We will learn in upcoming chapters. But for the time being, we can see the electrons from this region where the electrons were in excess now will go into the earth. Now, what will happen? Say, if this is our sphere, now negative charge is now gone into the earth. And suppose now we remove this wire. What will happen? The positive charge of this side will remain as it is, but some of this negative charge will go into the earth. Hence, here also deficiency of electrons will be there. So, what we are left with? We are left with a positively charged metal sphere. Now, we can see in this method, charging by induction, we took a charged ebonite rod, we took it closer to a isolated metal sphere. Now, after coming closer, the charges will get separated. We will connect negative part of the sphere with the earth, due to which some negative charge will flow into the earth. Now, as some of the negative charge from the sphere has gone into the earth, that will create deficiency of electrons on the metal surface, or we can say deficiency of electrons means excess of positive charge. So our sphere is now charged with positive. So this was another way of charging a material. Now we are in a position to discuss how we calculate the magnitude between two charges. Now, for this, we have a simple law called Coulombs Law. Coulombs Law. Coulomb was the name of a scientist, and the SI unit of charge is also Coulomb. Now, the force between two charges is given by 1 by 4 pi epsilon naught Q1 Q2 upon R square. Now, we will discuss in detail about the terms involving in this expression. Suppose we have two charges. This charge is Q1 and this charge is Q2. Now, suppose the distance between two charges is R. Hence, the Coulomb law says that the force of attraction or repulsion, which will depend upon these signs or nature of these charges, the force is proportional to the product of both these charges magnitudes and is inversely proportional to the square of distance between them. Now, what is this term? Here, epsilon naught is the Greek notation which is called permittivity of free space. The value of epsilon naught is 8.85 into 10 to the power of minus 12 Coulomb square by Newton meter square. Now, what does epsilon naught signify? It signifies the amount of resistance experienced by an electromagnetic wave by or while propagating through a medium. So, since it is the permittivity of free space, that is vacuum, it means it is the amount of resistance that an electromagnetic wave traveling through free space will experience. Now, this is also only a fact which is not of that importance to us. The important is the force F can also be written as K Q1 Q2 upon R square, where we have replaced 1 by 4 pi epsilon naught with K. Now, why do we do this? Because after putting the value of 4 pi and epsilon naught in this expression, the value of K comes out to be very simple and easy to remember as 9 into 10 to the power 9 Newton meter by Coulomb square. Hence, from now on, we will write force F is equal to K Q1 Q2 upon R square, where K is 9 into 10 to the power of 9 Newton meter by Coulomb square. Now, we will discuss some important points regarding Coulombs law. Points. Coulombs law describes forces between only two charges, but suppose the charges are more in number. For example, suppose this is our y-axis and this is our x-axis. This is our charge on which force is needed to be calculated. Suppose there are many charges. Due to this charge, suppose the force is F1. Since it's a vector quantity, we will represent it by vector. Suppose by this charge we have F2. By this charge the force is F3, and suppose this is nth charge, so suppose the force is Fn. So the net force on a charge will be vector sum of individual charges force. That is, this F can be written as vector F is equal to F1 vector plus F2 vector plus F3 vector plus so on up to Fn vector. Now, this particular statement is called principle of superposition. That means if number of charges are present, then to find the net force on a particular charge, we will just add them vectorically by individual forces and we'll get the result. Now, the second point to be noted is Coulomb force or force between charges is action-reaction pair. Action-reaction pair. What does that mean? Suppose we have two charges Q1 and Q2. Suppose due to Q2 charge, the force on Q1 is F1, and due to Q1 charge, the force on Q2 is F2. Also, suppose this is the line of joining of the two charges. Now, the meaning of an action-reaction pair is that forces are of equal magnitude, that is F1 magnitude equals to F2 magnitude. Second point is they are opposite to each other. Forces are opposite. Now, combining these two equations, we can also say the forces are equal and opposite. And the third and the most important point is that both the forces will act along the line joining the two charges. That means either the force will be like this or it will be like this, but it can't be away from this like this or like this, anything. Now, the third point about this force is the force is written by 1 upon 4 pi epsilon naught q1 q2 upon r square, where r is the distance between two charges and q1 q2 are the magnitude of charges. Now, this force is valid when charges are in vacuum. But what happens if we put it inside some medium? In that case, F dash force will be 1 by 4 pi k epsilon naught, where this k is not this k, but this is kappa, which is also a Greek letter. So, the force will be 1 by 4 pi kappa epsilon naught q1 q2 upon r square, where kappa kappa is the dielectric constant of the medium in which charges are placed, and this term kappa times epsilon naught is called epsilon. This is the permittivity of free space, where this is the permittivity of the medium. And hence we can say the net force after insertion of a medium is decreased by kappa times, where kappa is the dielectric constant. For example, dielectric constant of water is 81. We don't have to remember all the medium's dielectric constants, that will be given in the question. Now, we will discuss Coulomb's law in vector form. The force is given by K q1 q2 upon r square. Note that K here is 9 into 10 to the power of 9 Newton meter square by Coulomb square, and this is the force in vacuum. Now we are dealing with vacuum problems only. For another problems in which the medium is not vacuum but changed, it's mentioned in the question. Since force is a vector quantity, the representation of its direction also becomes important. Now, suppose we have one q1 charge here and q2 charge here. We have also seen that the force will act along the line joining the two forces. Suppose this force is F1 here and this force is F2 here. Now we can clearly see that the direction of force is the same of as the direction of r vector, that is the position vector. So we can write it as f cap, which is the unit vector along the direction of force, is equal to r cap, which is the unit vector along the position vector. Now also r cap is the unit vector, so it can be written as unit vector. By the definition, it means vector divided by its magnitude. Now if we represent this force in vector form, we will write F vector equals to magnitude k q1 q2 by r square into direction f cap. Since f cap is equal to r cap, we will write k q1 q2 by r square into r cap. Now since r cap is equal to vector r by magnitude of r, we can write it as k q1 q2 r vector upon r cube, where r is the magnitude of distance between two charges. We can further extend this force as F vector is equal to k q1 q2 upon, since it's the magnitude of position vector between the two charges, we can write it as r2 vector minus r1 vector magnitude whole cube into r2 vector minus r1 vector. We can't use dot here, this is not a dot product. We will write it as simply this. Understanding this from figure, suppose here we have one charge q1 and here we have another charge q2. Suppose the position vector of this charge is r1 vector and position vector of this charge is r2 vector. Now the distance between the two charges is r as per our derivation, so we will write this distance to be r vector. Now by vector law of addition, we can say r1 vector plus r vector equals to r2 vector, or r vector is equal to r2 vector minus r1 vector. And hence we can replace from this expression the value of r with r2 minus r1 and r vector with r2 minus r1 vector, which gives the final result be this. This is called Coulombs law in vector form. Now based on this law, we will take up a question. And the question says a fixed charge, a fixed charge Q is placed very far, very far from another charge, another charge Q. The charge Q is given a velocity v naught towards Q. Now, if the mass of charge Q is m, find the maximum Coulomb force, Coulomb force between the two charges. We are also given that neglect gravitational forces. Gravitational forces. First of all, we will understand this problem. We are given that one charge Q is fixed very far from another charge Q, which is given some velocity in the direction of charge Q. The velocity is v naught. Now, by seeing, we have to calculate the maximum Coulomb force between the two charges. Now, by expression of force in scalar form, we can see it's the F equals to kq by r square, where r is some distance. Now, we can see initially it was given the velocity towards q. So due to this, the distance between the two charges is decreasing continuously. After a certain time, due to both the charges having the same nature, that is q, and no one is negative, so they both will repel each other. So initially it was moving with velocity v naught towards charge q. After there will be a point when the repulsion will be so large that it will be able to repel the charge, and the charge will start going away from q. Now, if we are able to get this distance, that is x, which is the shortest distance, then since x is the minimum value, so this value is minimum, so in that case the force will be maximum. So this is the scheme. So our objective is to somehow find this value of x. Now we will remove some extra items. Yeah. Suppose at any instant the distance between them is x. Now, the net force between the four charges is at that time given by F equals to k q upon x square. Since no other forces are acting between the two charges, since we are given that, we have to neglect gravitational forces, because since charge is the intrinsic property of a matter, mass is also an intrinsic property of matter. So practically Coulomb force and also gravitational force both will act simultaneously, but since we are given that, we have to neglect the forces, gravitational So we will consider only Coulomb force. Now, since total net force on the charges is this kqq by x square, this is the net force on the charge q. Net force on charge q. The mass of charge q is m. So we will write this to be mass into acceleration equals to kqq upon x square. Now, for proper calculation purposes, we know since the force is repulsive, we will assign negative sign to it. Now, acceleration can be written as dv by dt equals to minus k q by x square. Using chain rule of calculus, we can write this as dv by dx times dx by dt equals to minus kqq by x square. Since dx by dt is the rate of change of the distance between the two charges, we can simply call it as velocity of charge q, that is v. So we can write this as mv dv by dx equals to minus kqq by x square. Further, we can write mv dv equals to minus kqq by x square dx. Now, we will simply integrate this equation. We can see initially we are given that is the fixed charge q is placed very far. So, that is the charge will tend to infinity. The distance will tend to infinity. So, initially x was infinity, and at that time the velocity imparted to this charge was v naught. So when x was infinity, velocity was v naught, and when there will be the point of shortest distance, this point, the velocity will be 0. So at some xm, that is x minimum, the velocity will be 0. Now, solving this equation, we can say mv square upon 2 v naught 0 equals to minus kqq into minus 1 by x infinite xm. Now, putting the limits, it will be m times 0 minus v naught square by 2 equals to minus kqq minus 1 by xm minus of minus minus plus 1 upon infinity. Since 1 by infinity is 0, we can write. So our equation becomes mv naught square by 2 equals to kqq upon xm. From here we get xm equals to 2kqq upon mv naught square. But this is not all. We have to find out the maximum Coulomb force between the two charges. So we have concluded that the maximum Coulomb force will act when the distance between the two charges is minimum, and that distance is this. So at that time, the Coulomb force F will be k qq upon xm square. Putting the value of xm here, we will get k q upon 2k q upon mv naught square whole square. This will be equal to kqq upon 4k square q square small q square times m square v naught power 4. Now simplifying this, we'll get m square v naught power 4 upon 4 k q q. So we will write the maximum force F max will be m square v naught power 4 by 4kq q. This is the maximum force between the two charges. Thank you, and we will continue in next lecture.